All right, so our second speaker today is Matthias Chen, visiting Newcastle from the University of Auckland. And Matthias is talking about PK closed groups acting on trees. Thanks, Matthias.
Thanks for having me. All right, so we're going to be talking about PK closed groups acting on trees. So we'll start with the setup, I suppose. Yeah, cool. All right. So we're going to be looking at groups acting on trees by automorphisms. And specifically, we'll assume that T is an infinite tree, but it's locally finite. So an infinite number of vertices, but every vertex has a finite number of neighbors. And we'll be thinking of graphs in sort of the sense of Serre. So we can think of this still as a graph with vertices and edges, but every edge we can think of as an arc and a reverse arc. So every arc has like a terminus and origin. Okay, so we'll get into the main property for this talk, which is PK, which is property PK. And so if we have a group acting on a tree, and we have some k in the integers, then the PK closure of G is defined as this sort of set here, which is a group. And so it's a set of automorphisms of the tree, such that if you look at sort of how those automorphisms act on a ball of radius k around each vertex, it looks like some elements of our original group G. So yeah, so there's sort of the set of automorphisms that locally look like G on all the vertices. On all the balls of radius k around every vertex. And so we say that G is PK closed or has property PK if G is equal to its PK closure. All right. So I'll give a little example of what that means here. So let's assume we start off with the binary tree, the infinite binary tree. So every vertex has two children and then so on and so forth. And we want a group that sort of acts on this tree by automorphisms. So I'll quickly construct one using sort of the generators. So we can take one generator to be sort of the automorphism that swaps those two vertices. And then, it'll like sort of swap everything underneath them as well. We can take the automorphism that swaps everything on that lower level. So it swaps the left two vertices down here, and then the left bottom right vertices down here, and at the same time. So you can't do them individually, you have to do them both at the same time. And then you can keep this going, you can go on the next level and then do everything, swap all the vertices on the next level, and so on and so forth. And so these will be the generators for our group. And now we want to look at sort of what do the PK closures look like for this group. And so I claim that this group that I've just generated is not PK closed for any k. And so why is that? So let's, for example, take the P1 closure. So remember the P1 closure is the set of automorphisms that on all the one balls around every vertex look like some element in our group G. So for example, let's take this vertex here, the left vertex, and let's look at the ball of radius 1 around it. And what can we do on it? What can the group G do on this ball of radius 1? Well, it can keep it the same. It can you can just do the identity where you move nothing, or you can also swap the two vertices down below here. Yeah. And and then we can take an automorphism of the tree that sort of swaps these two things here. And then everything else we can take as sort of fixed. And we're allowed to do that because around the ball of radius 1 on every vertex, we're allowed to have, we're allowed to fix everything because that's an element of our group G. And so this automorphism right here is an element of the P1 closure of G. But obviously it's not in G, right? And so the group is not P1 closed because the P1 closure is bigger than the group itself. And in fact, the P1 closure of this group will be just the full automorphism group on this binary tree. You can sort of see what that happens. And so it's not P1 closed. Is it P2 closed? Well, we can do basically the same thing. We look at this left vertex, and now we look at the tuple and take an automorphism that we're allowed there. So in this case, now I haven't drawn it up here, but we can actually just fix these two vertices here. We can swap these four down here, like this, like there. And then the rest of the tree we just keep fixed, and that there'll be an element of the P2 closure, but it's not, again, in G. And so we can sort of keep doing this for any K, and we'll see that it is not PK closed for any K. Cool, yeah. And so hopefully that gives you a bit of an idea of what PK closure sort of looks like. Yeah, so I'll give you some properties for PK closure. So if we have a group that acts on a tree T, and we take K to be some integer, some natural number, then we have that the PK closure of G is a closed subgroup, and closed sort of in the topological sense. And we're going to take a Fourier topology on the group to be the permutation topology. So two permutations in the permutation topology are sort of close together if they move a lot of points in the same sort of way. And so in this permutation topology, any group, including this group G, not just the PK closure of G, any group G and any subgroup of the automorphism group of the tree that's locally finite will be a totally disconnected locally compact group. And so this sort of this property, totally disconnected locally compact, is a property that people want to study. And so it's nice to have an example of groups with this property. And so this PK closure is a closed subgroup of this. And we also have that the PR closure of a group is a subgroup of the PK closure for all R greater than K. So the P2 closure of a group is a subgroup of the P1 closure. You can sort of see based on the definition why that's true, because everything that acts like G on the two ball will also act like G on the one ball, and so on and so forth. Yeah, and so basically, as you let K get bigger and bigger and bigger, you're sort of restricting the PK closure closer and closer and closer to G. And that's sort of shown in this final property that I'm showing here. If you take sort of like the intersection of all the PK closures, you eventually get the closure of G, the full closure of G. And so that's one of the reasons why we want to study PK closures, is we can sort of look, if we can take sort of ascending PKs, closures of groups, we can eventually look at how like all closed subgroups of like the automorphism group look like. Another reason why we want to look at PK closures is this theorem by Jacques Tits in 1970. If T is an infinite tree and G has property P1, or property P as he would have called it, and G doesn't preserve any like proper subtree or fix any end, then this subgroup that we generate from the stabilizers of edges is a simple group. And so with this property P, or property P1, we can get a simple subgroup from this. And this simple group is also totally disconnected, locally compact. And so it has this sort of nice property that we want. And so this was, Jacques Tits proved this for property P, or property P1. And Banks, Elder, and Willis in 2015, when they introduced this property PK as a generalization of property P, they proved basically the exact same thing, but for property PK instead of just property P. So you can get a simple subgroup from a PK closed group. And so that's part of why we want to look at these PK closures. Cool. So now we know why we want to look at the PK closures. Now, so we need a way to study. So we want a way to sort of study these groups that have this property. And so the first sort of step that was done towards this were local action diagrams, which were created by Reid and Smith, who are on this call. So So local action diagrams are essentially just labeled graphs. And so I've given an example here. We essentially have two vertices and an edge between them, or an arc and an arc reverse between them. And the way they're labeled is that for every arc, we give a set of elements called the color set. And then every vertex, we give a permutation group, and this permutation group acts on the set of points that point away on the arc sets for the arcs that point away from that vertex. And so this top vertex has the dihedral group on 4 elements on it, and it acts on 4 elements because, well, the arc pointing away from that vertex has 4 elements on it. And similarly for the bottom vertex, it's C3 acting on 3 elements because the arc pointing away from it has 3 elements. And so this is a local action diagram. And from this, we can construct a group acting on a tree. How do we do this? Well, if we let's say, call this local action diagram delta, we can construct what's called a delta tree. So for this local action diagram, the delta tree will look something like this. So I've also colored these edges with sort of half arcs. So this sort of half arc sort of represents that the arc pointing away from this vertex is colored red, and the arc pointing away from this vertex is colored purple, and so on and so forth. And so this is a delta tree. And you can see it sort of corresponds to this local action diagram because so for each vertex in the delta tree corresponds to one of the vertices in the local action diagram. So the central vertex is filled in because it corresponds to the filled in vertex here, and its neighbors to the non-filled in vertices, which correspond to the non-filled in vertex down there. And they correspond because this number of neighbors around each vertex is equal to the number to the color set of the arc that points away from it. So this has 4 neighbors because the arc pointing away from the filled in vertex has 4 elements in the color set. And you can ever color them with the color set. And so we have a tree that comes from our local action diagram. And then for a group that acts on this tree based off of the local action diagram, well, it's just the set of automorphisms of this tree. So that sort of map vertices to vertices that correspond to the same vertex in the local action diagram. So this vertex can only be mapped to things like this vertex. And when you map a vertex to a vertex like this, it gives a permutation on the colors on the arcs around it. And so the group that's associated with the local action diagram, the universal group, as it's called, is the set of automorphisms of this tree, such that these sort of induced permutations on the arcs around each vertex come from the the vertex groups that were given in the local action diagram. And yeah, and so from a local action diagram, we can construct a group acting on a tree. And we can do the other way around as well. If we have a group acting on a tree, we can construct a local action diagram from this group acting on a tree. And what Reid and Smith proved was that if you take the universal group of this local action diagram acting on its delta tree, this is isomorphic to the P1 closure of the group acting on the tree too. And so if the group was P1 closed, then basically if you take that P1 closed group, you can take its local action diagram and then its universal group will be isomorphic to the group itself. And so we sort of get a one-to-one correspondence between P1 closed groups and local action diagrams. And that's what was proven here. We get a one-to-one correspondence between isomorphism classes of local action diagrams and the isomorphism classes of P1 closed groups acting on trees. And so, this is a very strong theorem. This allows us to sort of study, if we have a group that's P1 closed, then we can sort of take it to its local action diagram and study what things happen here. And if we want to construct a P1 closed group, we can just take a local action diagram and then construct a P1 closed group. And yeah, So this is obviously very strong, but we want something for not just for P1 closed groups, but for PK closed groups in general. And so local acting diagrams aren't quite enough. And so what we need are what we call graphs of group actions. And so graphs of group actions are something that was constructed somewhat recently. The paper with the construction of graph group actions just came out like a week or a few weeks ago on arXiv. So yeah, if you want to find a few more details about that, you can go check it out there. But I'll give a definition here as well. So graph group actions is very similar to a local action diagram in that it's just a labeled graph, but there's a few differences. So first of all, we have obviously our underlying graph for the graph group actions. But now for each vertex, we give a permutation group. And so we give a group, and we also give us the set that the group acts on. So that's part of the label for the vertex. So each vertex gives a group and a set the group acts on. And then for each arc, we also give a permutation group. We give a group and then the set that the group acts on. And we require that for each arc, the arc reverse has the same label. And lastly, we need, we give an embedding. So we give an embedding from an arc, from an arc set into the vertex set for the vertex that the arc points to. So sort of the terminus of A. So, and we require that this embedding sort of respects the group action. And so it's sort of a permutation group embedding. And so this is the information that we need for a graph of group actions. If you've seen Basser theory and graphs of groups, this is defined in a very similar way, but there's some differences, but don't ask me about that because I don't know all the details. Anyway, yes. So this is what we need for graph of group actions. Yeah, and so I'll give an example here. So it's a very similar graph to what we had in our local action diagram example. We have two vertices and an edge between them, or an arc and an arc reverse. And now we have that label on this left vertex is a dihedral group acting on 4 elements, and we have the set of 4 elements in our vertex label. And then the same thing on the right, we have a group of the symmetric group of 3 elements acting on 3 elements, and we give the 3 elements in our vertex label. And now for the arc, I've only given the label for one arc, but as we stated in the definition, the arc and the arc reverse must have the same label. So the bottom arc will have the same label as well. And this is the symmetric group on 2 elements acting on 2 elements. And so so this is graphs of group actions. Again, very similar to local action diagrams, just a labeled graph. And so again, we want some way to translate this into a group acting on a tree, right? And so yes.
So just a second. So on top of this graph, we also need the embedding information, right?
Yes.
For which there could be different options.
There are different options, yes.
Yeah.
Although, we can just say that the 2 elements will embed into 3 elements and then 4 elements in some way. We don't need to specify it right here. But as long as it sort of respects the group on both, on the arc and the vertex. Yeah. So this is our graph of group actions. And so we want some group acting on a tree from this graph group actions. And so for that, we need one final thing that I want to define, which are these adhesion sets. And so adhesion sets are just translations of our embedding under the group action. So when we embed these points, these arc sets into the vertex sets, the group action can then sort of translate that set around. And so these sort of translations are the adhesion sets. And so if I give an example here, so let's say that the 2 vertices, so let's say this set of 2 embeds into this set of 4 in this way, right? So this is the image of the embedding. And now if we translate it under the dihedral group, in sort of the way that makes sense. This is a square. So the translations of this image will look like this. And so these will be the adhesion sets. So we get 4 adhesion sets for this sort of arc. All right. So now that we've defined that, now we can get into sort of the tree-like graph that we want to sort of act on. So we won't necessarily get a tree. We'll get something which we call a scaffolding, which is a bit more complicated, but I'll sort of talk you through it. So it's essentially scaffolding is essentially just a graph, but it's a graph with the equivalence relation on vertices. So I'll give you the scaffolding for this graph of group actions, sort of given here. But to make it easier, I'll put the equivalence put the equivalence classes in as sort of these circles. So this is a scaffolding with the equivalence relations shown. And there's a few things that we want to note to make sure that this is a scaffolding of our graph of group actions that we gave previously. So first of all, if we took sort of each equivalence class to be a vertex, then squished all the vertices in equivalence class down to one vertex, and then connected each equivalence class if they were connected in our scaffolding, then this sort of squished down graph that we get is a tree. You can sort of see that we sort of get like a tree-like structure out of this graph of group, out of the scaffolding from the equivalence classes. We then need to make sure that every sort of equivalence class sort of looks like a copy of one of our vertex sets. So the central equivalence class here has 4 vertices in it, which sort of are in bijection to the set of 4 elements on this vertex here. And then the same thing for each of these equivalence classes next to that central equivalence class. They have 3 vertices within them, which are in bijection to the set of 3 points here. And so as long as we have these sort of few key, I guess, axioms. We also need to require that these equivalence classes are connected by the adhesion sets, right? So remember that this adhesions, this was the blue and the yellow was the adhesion set, was one of the adhesion sets. And so we connect it to the adhesion set in the other vertex group. And we connect these equivalence classes through their adhesion sets. And so as long as we sort of follow these axioms, whatever graph we get with the equivalence relation is a scaffolding of our graph of group actions. And so we now have a tree that sort of is associated with our graph of group actions. We now want a group that acts on this tree or this tree-like structure. And so we can for what we want for the universal group, for our graph of group actions, we now take the set of automorphisms of this graph that respect the equivalence relation. So it sends these equivalence classes to equivalence classes in a way that makes sense. And the last thing that we need is that when this, for example, this equivalence class in the center with 4 vertices gets mapped to this equivalence class with 4 vertices up here, it again induces a permutation on the 4 vertices. And so we say that the universal group is a set of automorphisms that respect this equivalence class. We also want to make sure that these sort of induced permutations that we get when we map equivalence classes to equivalence classes are elements of our vertex groups in our graph of group actions. And so this gives us a group that acts on this scaffolding. And since we can sort of turn this scaffolding into a tree, we then get a group acting on a tree that comes from our graph of group actions. And so, yeah. And so with this, we get group acting on a tree. And so last thing, well, not the last thing, but, and so the thing that we can now, the thing that I've sort of, what I've managed to sort of prove is that if we have a group acting on a tree, then there exists a graph of group actions such that its universal group acting on the scaffolding tree is isomorphic to the PK closure of the group, of the group acting on it. Yeah, so this is what I've managed to prove so far. And I'll give you, and for sort of this next part of the talk, I'll sort of try and give you sort of an understanding of like how this theorem sort of works. So, yeah. So let's perhaps start with a group acting on a tree. So let's say the tree is sort of the biregular tree of 4 and 3. So there's a bunch of vertices of degree 4 and vertices of degree 3, and vertices of degree 4 are neighbors to vertices of degree 3, and so on and so forth. So this is an infinite tree. And the group acting on this tree, we don't actually need like too many details about what this group does on the tree. All we really need to know is the orbits of what the group does on the tree. So we'll say that the group acts transitively on the vertices of degree 4 and transitively on the vertices of degree 3. So we'll have sort of two vertex orbits, a vertex orbit of vertices of degree 4 and vertices of degree 3. And now we want to try and construct a graph of group actions whose universal group is the PK closure of this group. And so for this example, let's say we want the P2 closure. So we want all the orthomorphisms on this tree that sort of acts like G on all the tuples of the tree. So first we need an underlying graph. And so if you've seen this done for local action diagrams, where if you start with a group, you can construct a local action diagram. This is essentially a very similar sort of strategy here. So the underlying graph that we want is the quotient graph. So every vertex of the quotient graph is a vertex orbit under the group, and there are also the arcs orbits, and they're connected in sort of the way that makes sense. So the underlying graph will look something like this. We have two vertex orbits, and they're connected because there are arcs between the vertices degree 4 and vertices degree 3. And so this is the underlying graph for our graph of group actions. And now we want to label the vertices and the arcs. And so for the vertex labels, we'll take these groups, and I'll sort of try and explain what they are. So we're taking, on this left here, let's assume this left vertex represents the vertices of degree 4, and the right vertex represents the vertices of degree 3. So what we're taking as the vertex labels here are sort of what the group G does on the tubules around the vertices degree 4. So I'll make that more concrete. So we're taking GV as the stabilizer of G on a vertex of degree 4, restricted to its action on a bowl of radius 2 around that vertex. So we're taking just some vertex of degree 4 and then doing this. And then we're going to do the same thing for the other vertex as well. So we take the group, and then the set will just be the tuple around that vertex. And the same for the other thing. And then for the arc label, we'll give, now instead of taking a bowl around a vertex, we'll take a bowl around an arc. And so we'll take the bowl of radius 1, not 2, so 2 minus 1, and n minus 1, k minus 1 in general. And so we'll give this arc a label, and therefore the arc inverse a label. I'm sort of hand-waving a lot of this because how we choose the arc vertices and arcs is quite complicated, but I'll sort of sweep a lot of this under the rug. So this is the arc label here. And the embedding is sort of I guess hopefully it's obvious. You can sort of see that this bowl around the arc clearly embeds into sort of a bowl around the central arcs here, and same for in this bowl here. And so we have sort of a natural embedding into the bowls of radius 2 of this sort of arc set. And so this is our graph group actions. I claim this is the graph group actions that we want. And so what we need now is to prove it. So I'm going to first do something maybe seemingly a bit weird, but hopefully you'll see what I'm going to be doing. So now we want to prove that the universal group of this acting on the scaffolding is isomorphic to the PK closure, the P2 closure in this case of G. So what I'm going to do is I'm going to take our original tree T, and what I'm going to do is I'm sort of going to split apart the bowls of radius 2, or sort of like, I'm not sure the right word for it, but sort of split apart the bowls of radius 2 around every vertex. And so we have a bowl of radius 2 around this vertex, we have a bowl of radius 2 around this vertex, and then bowl of radius 2 around basically every vertex. And we're basically going to split them apart into something that looks like this, right? So we now have a bowl of radius 2 around our central vertex. We have a bowl of radius 2 around like each of its neighbors, the vertices of its neighbors, and then so on and so forth. We have bowls of radius 2 everywhere. And so we have bowl of radius 2 for every vertex in our tree. And now we connect neighboring bowls in some way. And in some way, I'll say specifically how they're connected. They're connected by sort of the vertices that were, by sort of a matching between the vertices that were set, that are sort of the intersection of the bowls, which are basically, so we're essentially creating a matching between vertices that used to be the same. So in this case, so we're sort of connecting vertices that used to be the same in our sort of original tree, and now we're sort of stretching them out and connecting them along by a matching. And so we're doing this for every vertex and every bowl of radius 2 around every vertex. And what hopefully we can see happens here is that this is actually a scaffolding of our original, of this graph group actions that we constructed. Why is that? I mean, you can first see that this sort of thing, this sort of like, if we take this as the equivalence relation, basically, so every equivalence class is one of these like bowls of radius 2, then the graph that we get by sort of smushing all the vertices into one vertex for each equivalence class, this graph that we get is a tree. And in fact, this smushed down tree that we get is actually the tree that we started with, because for each vertex, we sort of took the bowl of radius 2 around that vertex, right? And then we connected them through their neighbors. So this sort of scaffolding tree that we have is isomorphic to our tree that we originally had. And this is also scaffolding because, I mean, you can see for every equivalence class, we have a copy of a bowl of radius 2 around a vertex. And in our graphic group actions, our vertex sets were bowls of radius 2 around vertices. And so in each equivalence class, we get a copy of a bowl of radius 2. Okay. And then the last thing is we connect them along these adhesion sets. And so if you recall, the equivalence class, the adhesion sets are sort of images of this sort of bowl around the arc here. And we connected them in essentially the same way, right? Using these bowls around an arc. And so we get that this is a scaffolding of our initial graph group action. And so, and then the scaffolding tree is the tree that we started with. And so, and so we've shown that the tree is the scaffolding tree is the tree. And so last thing we need to show is that the universal group of this graph of group actions is the PK, or at least in this case, the P2 closure of our initial group G. Yeah. And so the key observation here that we want to note is that if we sort of take an action, if we sort of take an action on this bowl of radius 2 here, it will actually extend out to the same action on the bowl of radius 2 on this entire big scaffolding tree. And that happens because when we split the trees apart and connected them up, we connected them up based off of when the vertices were the same, right? We connected them along their intersection, which was when the vertices were the same. And so if we moved this sort of vertex here, it would connect to the center of like this vertex here through sort of like a path you can sort of see. And so what happens in this central vertex will happen on the whole bowl of radius 2 in this big tree here. And so the local actions in our equivalence classes will propagate out to the actions on the actual scaffolding tree, which is, again, our tree from our original group. And we defined our graph of group action, our universal group, to be the set of orthomorphisms of this tree, where on every equivalence class, it looked like our, on every equivalence class, the permutation induced was a permutation given from our initial graph of group actions. And since the initial graph of group action, in our initial graph of group actions, the group for this equivalence class was essentially just how the group G initially acted on the bowl of radius 2, then we get that this universal group is the P2 closure. Yeah. And so hopefully that, maybe that wasn't completely clear, but hopefully that was good enough for now. Yeah. And so we get that if we start with a group acting on a tree, then we can construct this graph of group actions such that the universal group acting on the scaffolding tree is isomorphic to the PK closure of T. Because we can do essentially the same what we did for the P2 closure of that group. We can do that for any PK closure for any group acting on a tree. And so namely, we get that if G was PK closed, then the universal group will be isomorphic to our initial group acting on a tree, on a tree too. All right. Yeah, I think that's almost all of what I had. So lastly, I'll talk a bit about work in progress that we're doing right now. So obviously that's sort of just one part of the correspondence the full correspondence that we have between local action diagrams and groups and P1 closed groups acting on trees. And we don't have that full one-to-one correspondence between isomorphism classes in the PK closed setting right now. What I've proven so far is sort of one step in that correspondence, but we do want a full sort of correspondence. And there's a few problems that arise when we try it, when we try to do this, like for all like isomorphism classes of graph group actions and isomorphism classes of PK closed groups. The main thing is that, there are potentially two non-isomorphic graph group actions that give you the same PK closed group acting on a tree. That's potentially something that can happen. And so we need to sort of figure out a way to sort of create a nicer correspondence. And so we probably need to restrict what types of graph group actions we need to look at, something along those lines. But we're still working on that. And the final thing that we're sort of working on right now is in terms of like sort of related to this PK close stuff is the enumeration of PK close groups. And so when we had the correspondence of local action diagrams and P1 closed groups, we were able to use that correspondence to enumerate all the P1 closed, all the P1 closed groups for vertex transitive groups, P1 closed groups acting on trees. And that'll probably be expanded further later on. And so we want to do essentially the same sort of enumeration, but for PK closed groups. But that sort of relies on this full correspondence that we previously have. But we are still also sort of partly working towards this, like doing some programming and stuff to sort of get this up and running. And this enumeration will also be really nice because if from what I said previously about sort of the like intersection of all the PK closures of a group, if you sort of take that sort of string of intersections getting K larger and larger and larger, we'll eventually get to the closure of the group itself. And so this enumeration of PK's closed groups will sort of allow us to sort of look at how closed groups in general on a group for groups acting on trees would sort of look like. By sort of looking at the sort of string of P1 and the P2, P3 closure of like each of these groups. And so this enumeration would hopefully give us sort of a better idea of what these sort of closed groups are. I think that's all. Thanks.
Thank you. All right, questions or comments for Matthias? Well, we maybe go back to the picture of that the big tree you drew. Yeah, this one.
Yes.
Yeah. So I'm just trying to remember now. So for example, the fact that the central bubble here has 4 neighbors is due to the fact that the other bubble has 4 different adhesion sets inside.
Yeah, I mean, well, it's because this bubble, because this bubble has 4 adhesion sets for the arc, right?
So does that rely on the group acting locally transitively to get those 4 adhesion sets?
Yes, that would be that is because that is locally transitive on the arcs. If we had more edge orbits, we'd have to add more arcs.
Oh, yes,
in the
yes,
graph
of
of group
course. Yeah,
actions.
makes sense. Yeah, the quotient graph was just 2 vertices and 1 arc, so they're
Yes.
all in 1 orbit. Yes,
Exactly. But if there were more edge orbits, we'd have in the quotient graph, we'd see like multiple edges between the 2 vertices.
Yeah.
And so or I guess maybe between more different vertices, not sure. But yeah. And so that depends on the number of adhesion sets around the central vertex.
Yeah. Thanks. Did anyone else have any?
Yeah, I have a question.
Yes.
Thank you. That all sounds very nice. I'm just wondering about some of the other ideas in Colin and Simon's papers, whether they carry over. So, for example, they relate structures of the graph of the local action diagram to properties of the group. And I'm wondering whether, well, I guess you'll be able to have the same group properties and relate them to structures of these of your refined local action diagrams. But do the classes of structures that are identified, do they get refined? So you get a sort of finer description of the relationship between properties of the graph and properties of the group?
Yes, we should. This is more the domain of Florian, my supervisor, who's also working on this stuff. But yes, we should see the same sort of like ideas of like if we look at properties of our graph of group actions, we should be able to say stuff about properties on the tree that we get from it and vice versa and stuff. Yeah, I mean, Florian, he has this meta conjecture that says that everything that works for local action diagrams works for graphs of group actions. So yeah, we're hoping that's true, and it seems to be doing all right so far. I think we've looked at some stuff like you can compute things like the scale function of a graph acting on a tree using its local action diagram, and we seem to be able to do or at least we're trying to, we look like we might be able to do something similar with the graph group actions, I think, so far. Yeah. And yeah, a lot of other things, hopefully, we'll also be able to translate over. Yeah.
Right, okay, thank you.
Yeah, I have a question as well. Thank you, Matthias. That was really interesting. I liked it a lot. I missed the very beginning because my Zoom crashed. And when you were defining PK closure, were you only talking about locally finite trees, or?
Yes. For now, we're just talking about locally finite trees.
Okay.
I'm not. Yeah, I have to think about what what it means for a locally infinite tree, but
Yeah, because the definition of PK closure, I mean, it's equivalent in the locally finite case, but you need to be quantifying over finite subsets
yes.
of these balls, and then you get a group that's closed. But I was wondering how much of what you talked about today carries through to the non-locally finite case,
I'm
or is
not sure.
that still kind of up in the air?
Yeah, I think that's a bit up in the air right now.
Okay, cool.
We're sort of treating everything as locally finite for now. In the future, we'll probably look into something like this, but for now, we're not sure. Sorry.
Okay, cool. Thank you.
Yes, any more comments or questions?
So I was going to ask the same question as Simon about locally infinite trees, but something that's occurred to me. So there's a paper by Sam Shepard from a few years ago called Two Generalizations of Layton's Theorem. And I wondered if you or your collaborators had heard about this paper.
I haven't heard about it, but I'm not sure if other people have.
Okay, so in the paper, basically, he describes groups constructed from what he calls graphs of objects. And I'm not sure it's explicitly claimed in the paper, but he more or less says that you can represent PK closed groups this way. So I'm wondering if, like, what the exact relationship is between Shepard's construction and the graph of group actions construction.
Yeah, I'll definitely have to look into that then.
Yeah, so I'll email the link to you and the graph of groups authors.
Yeah. Sounds good. Yes.
Can you include me as well, please, Colin?
Yep, I'll email you as well, Stefan. Simon, did you want a copy as well?
I think I might already have a copy from when we were
Yeah, I think
corresponding with
Simon and I have
Sam, yeah.
discussed this paper at some point, but yeah.
Yeah.
Can you send the link to me as well, please?
Yeah, and I actually, so I talked to Sam Shepard a few months ago, and he wasn't aware of our work on local action diagrams. So,
Right.
yeah.
Thanks for pointing that out, Colin. Anyone else? If not, then we thank Matthias again.